three eminent speakers. One is Dr. Ujjal K. Gautam, second one Dr. Minju Porel, third one Dr. M.V. Nandakumar. The first talk is by Dr. Ujjal K. Gautam, who is currently working as Associate Professor, Department of Chemical Sciences, IISER Mohali. He did his master's at IIT Delhi, and after completing his MSc, he joined for his PhD degree at IISc Bangalore. And after his PhD, he moved to National Institute of Material Science, Tsukuba, Japan, for his postdoc studies. Then he joined as ICYS tenure track independent researcher, National Institute of Material Science, Tsukuba, Japan. Then after that, in 2011, he joined JNCSR Bangalore as a Ramanujan Fellow. Then currently he's working as Associate Professor at IISER Mohali. Going through his biodata, when seeing this is it seems that he's a very dynamic person and very apt person for this talk. He has several patents, almost 7 patents and 2 book chapters to his credit. And looking at the publications, he has more than 125 publications with big impact citations of around 9,400. And with this brief introduction, I invite Professor Dr. Ujjal K. Gautam to deliver his talk. Thank you.
So first of all, thank you very much for the kind introduction. Also to Farook College, Sir Professor Pradeep, and whom I know from my student days. And it is such a great pleasure to be here in Old Calicut. So I didn't know this place is actually Calicut. Only last week I got to know. And it was a long time plan that we'll come to Calicut sometime. So thank you for the invitation. Today I am going to talk about something a little offbeat. And I'm going to discuss about catalysis and sustainability using a particular catalyst called the Sillen Aurivillius phases. Okay? And I'm going to explain, present a unique phenomenon that we have discovered in our laboratory. Is called self-activation. So if you want to bring perspective to the talk, can you ask this question? We use catalyst in chemistry, we use catalyst all the time. And we know that catalyst goes bad with time. If you go to organic laboratories, catalyst is not usually recycled. It is used one time and thrown. If you go to the industry, it is recycled, but it goes bad with time. The question in this perspective, on the other hand, when you use heterogeneous catalysis, which means we use solids, one advantage is that we can recycle the catalyst. But the problem, what happens is that the catalyst gradually goes bad as you increase use more and more. So the question I'm trying to address here is that, is it necessary that a good catalyst deactivates with time? So in this point, the word good is important. What I want to emphasize is that you make a catalyst which is already very, very good, working fantastically. But is it possible that it doesn't go bad, but it keeps increasing, improving with time? So I'd like to acknowledge the funding agencies. And the work that I'm presenting here is particularly done by these 2 students, Maksuma and Arjun. So we use Sillen Aurivillius phases for 2 kinds of experiments, piezo-catalysis and photocatalysis. So I'm going to explain self-activation. I'm going to talk about 2 different reactions where I'm going to prove that self-activation is possible. But before that, I want to introduce another concept which is emerging at this moment, is something called piezo-catalysis. Photocatalysis, as you know, is harvesting of solar energy, solar light, and do some chemical reactions. In piezo-catalysis, the idea is to harvest noise or sound to carry out experiments. So what you need in this case is that you know that why a bomb works, okay? When the bomb explodes, there are many things, but one of the things is the sound. Sound can exert a lot of pressure. And when it exerts pressure on a non-centrosymmetric system, a crystal, it behaves like a piezoelectric material, which means that if you have a piezoelectric crystal and if you throw sound into it, it develops charges on different facets of a crystal, which can be used for catalysis. If you have negative charge, it is going to do a reduction reaction. If there is a positive charge, it can do a oxidation reaction. So we have been using these materials to do piezocatalysis in our laboratory to produce hydrogen, green hydrogen. So I'll just show you some key results in this case. So this is the first paper where we have introduced these Sillen Aurivillius phases for piezocatalysis for the first time. When you do water splitting, that means we produce hydrogen and oxygen from water. One of the difficulties is that we use pure water, and pure water is not good because it is very, very expensive. It is expensive than alcohol, the kind of water that we use in our laboratory. On the other hand, if we can use seawater, which is plentiful in nature, but it poisons the catalyst because it has many impurities. So this is the first paper on piezocatalysis combined with seawater splitting, where we show where from the deactivation of the catalyst comes. But despite that, we can get good activity. I just want to explain quickly what happens. As you can see here, this is a crystal, and when we put sound waves, in this case ultrasonic sound, it develops positive charges and negative charges. Now you see that if you see within the crystal, if you see the electrons towards the positive charge and electrons towards the negative charge, now towards the positive charge what happens? The electron gets pulled down. So they have a lower energy. On the other side, because of electron-electron repulsion, they have higher energy. As a consequence, within the crystal, if you assume this is the crystal, the energies bend. It's called band bending. So this is the conduction band and this is the valence band, or you can say this is the LUMO, this is the HOMO. They bend within the crystal. As a consequence, you can use any material for oxidation and reduction reactions because you are not limited by the reduction potential of your catalyst. Because the reduction potential changes when you put pressure. It changes automatically. So if you have a centrosymmetric material, non-centrosymmetric material, if you put pressure, you can use it to do oxidation and reduction reactions. So in this case, again we introduce another concept. We want to remove pollutants from water. We want to degrade pollutants, organic pollutants, which means that we want to convert them to carbon dioxide. And this is again the first paper where we introduce both photochemistry and piezochemistry, we put them together. We should remember that when we do piezocatalysis, the electrons do not go to the excited band or LUMO. It is always in the HOMO. So it is a valence band phenomena. Now when we combine photochemistry and piezochemistry, we combine both excited state phenomena as well as valence state phenomena. So in this case, when you combine both of them, we end up getting something called synergy. So this is a very interesting paper. We have figured out the origin of synergy, where from it comes. There are about 7 independent factors which contributes to this synergy. So once we understand what happens, we have used it for pollutant degradation. The main difference compared to the conventional work is that we use pollutant feedstock, which is what you get in industrial concentrations, very high concentrations. This is another very interesting work, again about green hydrogen production. You see that this is a plot showing we have hydrogen evolution, and this is used for a very long time. Okay, normally it stops somewhere here, okay, but it shows some degradation. So this, using this Sillen Aurivillius phases, again I am not going to the details why it happens. It is something called space charge neutralization, something what happens in these crystals. So you get hydrogen evolution for a very, very long time. All right. So the last slide I'm going to show about piezo-catalysis is that I just mentioned that we have to use a non-centrosymmetric system. But majority of the materials that we have are not heavily non-centrosymmetric. They're not heavily polar. So if we can use non-polar systems and we can still do piezo-catalysis, this is excellent. And if we want to do this, we somehow have to introduce non-centrosymmetry in the system. So in this case, is about introducing vacancies within a centrosymmetric crystal. This is a BiO-BR crystal. I'll come what is BiO-BR. So when you introduce oxygen vacancies, these unit cells become polar. So you can control the amount of vacancy and you can introduce, you can generate large amount of green hydrogen. The other reason why this paper is important is that we have positive charges and negative charges. The positive charges, the negative charges will give rise to hydrogen because it reacts with a proton. The positive charges give rise to oxygen, which is not good, is not very useful. Oxygen is not useful. In this work, again, for the first time we saw that we can get hydrogen and hydrogen peroxide on two sides of the crystal. So you see now we have two fuels getting generated at the same time. Okay, and another, again, important point, when you produce hydrogen and oxygen, you have to separate them if you want to use hydrogen. In this case, because hydrogen peroxide remains in the solution, you do not have the problem of separation. Okay, so you have two fuels generating at the same time, but you do not have to separate them. All right, so I'll briefly introduce what is Sillen Aurivillius phases. As the name suggests, it has two components. There is a Sillen part and there is an Aurivillius part. So you can see here, this is the last paper that I said, BiOCl or BiO-BR, with a general formula. This is a layered material. We have Bi2O2 layers separated by halide layers. Okay, so this is the Sillen phase. This one is an Aurivillius phase. This is based on perovskite structure. This is a perovskite structure, okay, but separated by Bi2O2 layers. Now you can see these structures are somewhat similar. If we can combine them, okay, if we can take out this part and mix it with this part, we end up getting something called Sillen Aurivillius phases. These two phases were known for about, say, more than 100 years. These phases were discovered in 1985, and fantastic systems because they are structurally very diverse. You see, this is a complex formula. We'll not go into the formula, but what you know from here is that there are a lot of variables here, and if you keep changing the variables, you can get many, many different crystals. In this case, for example, a Sillen Aurivillius phase, a single layer phase, and a double layer phase, meaning that it has two perovskite blocks together. Now this phase become very interesting from this particular paper, which came in 2016 from Japan. Now what happens, if you take the Sillen phase, only BiOCl phase, this is a very good photocatalyst. But its stability is not good. And the reason is the following. If you look at this band structure, okay? If you look at this band structure, you have oxygen and we have chlorine on the valence band, and we have metals in the conduction band. Now, when these electrons get excited, it gets excited from chlorine. So if chloride gives one ion to the metal, it becomes chlorine and it comes out very easily. Which is difficult in case of oxygen because oxygen has to give 2 electrons. Chlorine has to give only 1 electron. So instead of chlorine, if you have oxygen here, this will be much more stable. Now if you look at metal oxides, okay, metal oxide, the valence band is made of oxygen, not of chlorine. So these are stable. But the problem with oxides is that they are normally white. They do not absorb sunlight. BiCl absorbs sunlight, but it is not stable. But when you mix them together, because of the changes in crystal structure, what happens is that these oxygen p bands, they get flattened out, or say they expand. So this is the schematic. These are some theoretical results. But essentially what it means is that now we have a structure where the band gap is very similar to BiOCl or the Sillen phases, but the valence band consists of oxygen, and therefore it is stable. Therefore, this was used for water splitting with very high efficiencies. So I'll skip most of the synthesis parts. We can synthesize them in various ways, but they are very beautiful. This is what I wanted to point out. You can see that they are single crystals. They are tiny single crystals. This is a high resolution image. You can almost look at the atoms here, or the rows of atoms, okay? If you look at the electron diffraction pattern, it again confirms that they are single crystalline, very beautiful structures. Then once you have a single crystalline structure, we know that crystals have different facets. In this particular case, this crystal has 001 facets, which is the bigger face, and which is responsible for 001 phase is the polar axis, and this along which the reaction actually happens. All right. So let me introduce something about dye degradation reactions. I guess some of you might be familiar with this reaction. It's a very, very simple reaction. It is so simple that almost anybody can do it. You can do it in sunlight, and you can observe it with your eyes. So you do not need instruments. And that's why you see a large number of papers coming in this area. So the motivation in this case is that these dyes are very cheap. A dye can be a dye only if it is cheap. The second quality a dye must have to have is that it is very stable. Otherwise, nobody will use it as a dye. The problem, because it is cheap, everybody throws the dye after use. Now, if you throw it, it goes to waters and it gets waste. Now, photocatalysis is something very interesting, because in photocatalysis can oxidize these dyes and convert them to carbon dioxide. Now, what happens in the process is that suppose if you have dirty water, it will become clean. So in this way, you can clean waters. So this is one such example of dye, is called rhodamine B dye, which is probably the most widely used dye in the textile industry. So last 55 years, these experiments has been going on that we make catalysts which can degrade this dye very, very fast, okay, as fast as possible. And we have similar works. We did some similar works, but I'm not going to talk about that. The question that we want to ask is that if you want to clean water, you want a very good catalyst. You want to make it very, very fast. So I want to draw your attention to this question. Why should we make dye degradation slow? We should remember that when we make it slow, the water decontamination is going to be very, very slow. Despite that, why should we make it slow is the question. And in my opinion, dye degradation is not useful because you have lots of paper, roughly 300 papers, I think, per week or something like that. But it is not useful because you have very little dye, you have large amount of photocatalyst. The second problem is, so you have to use large amount of photocatalyst. Now that photocatalyst, if you put it, for example, in a river, there is no way you can recollect it. It goes and it itself becomes a contaminant. So it is not very useful. So let's ask this question, why should we make it slow? So now this is a reaction, and you can see this has gone all the way up to 800 minutes, which is roughly 15 hours. Okay, it's a very, very, so typical time is 15 minutes. So this is 15 hours, very, very slow reaction. We made it slow. What you see in the process is that you see some color changes. There are beautiful color changes. The red color, the pink color has gone through green color, and the color disappears. Okay? So before, conventional system is 15 minutes, and this is about 15 hours. Now, let us see this. What are these two colors? Okay? There are many intermediates, but if you see the last compound and the first compound is something very similar. Okay? The molecular structure is similar, except the fact that we have 2 nitrogen atoms, but these 2 nitrogen atoms are connected to 4 ethyl groups. The reason is that the nitrogen atom is very reactive. So if you leave the nitrogen atom as it is going to be reactive, and it cannot be a dye. On the other hand, rhodamine 110 is a very expensive dye. It's because it is reactive, and it is used in diagnostics. For example, if you put it in your body, it forms amide bonds with proteins, And when it forms amide bonds, the molecules can twist. And when a molecule twists, its color goes away. So it's something called profluorophore. So what you essentially see is that if you make this process slower, you start seeing what happens in between. And if you see what happens in between, you end up getting something which is very, very expensive. So if you can extract it, so dye gets converted to something very useful. So I explained what is profluorophore. When it forms these amide bonds, the molecule twists and it is no more fluorescent. So it's a probe. So normal synthesis of rhodomine 110 is expensive again because it is very reactive. You get roughly about only 5% yield. The rest of them are byproducts. So you have to clean them. So it becomes very expensive. These are something about the two dyes. We get about 35%. Okay, and we confirm that this is a completely pure dye. When you buy from market, even the purest dye is only about 99%. So this is nearly 100% pure dye. We looked at the mechanism. When you looked at the mechanism, what you see is that rhodomine B, this is a mass spectra, and you see there's a series of peaks. Now, when you see it, the molecule, it slowly loses its mass in a very typical fashion. And if you look at here, every time it loses minus 38 mass. And 38 corresponds to a methyl group. So essentially what happens is that different methyl groups keep going away, and which you can see because it's a slow reaction. Okay? At the end of the day, literally at the end of the day, because it is about 8 hours reaction, you start at rhodomine B and you end up with rhodomine 110, which is pure. Well, I'll skip this one. There are more studies. This is the detailed mechanism. It can go via multiple intermediates. So we figured out what is the actual mechanism. We'll skip that. But this is what I wanted to highlight is that you get about 35% yield. The rest, 65, still becomes CO2. This is on day one. But if you start using it, by the 30th day, you see you nearly get 100% yield. Okay, everything converts to rhodomine 110. And this is very good. Then we can increase the concentration by 5 times. We can increase the amount of dye that we are using. So if you put all of them together, it is roughly 7,500 times improvement. Okay, and we can get solid products which we can separate out. Okay, then I'll come back to this one later. At this point, I wanted to emphasize is that this molecule, when you look at this molecule can sit on a catalyst surface 2 ways. You can see this is as if it is touching the catalyst through its hands, the 2 ethyl molecules. The other possibility is that it stands upside down. Okay? When it stands upside down, it converts to CO2. If it stands something like this, one ethyl molecule keeps getting removed from this nitrogen. Okay. Now, what happens in this process, when you do the reactions, the bismuth oxygen bond is weak, and bismuth and oxygen keep getting leached out to the solution. When that happens, we have defects on the surface, and these defects are negatively charged. And because this nitrogen is positively charged, it gets attracted and it sits in this inverted position, and that's why this deethylation happens. Now, as the time passes, the leaching is more and more. As a consequence, more and more molecules sits in this position and the self-activation happens. All right. I'll go to another product. So this is one experiment we saw. The next experiment where we saw the same thing is hydrogen peroxide production. As you know, hydrogen peroxide is an important fuel. It's used in rockets. It's used in multiple industries. And again, when you synthesize this, it is not carbon neutral, okay? It uses a lot of energy. So the idea in this case, so this is the conventional method. Again, I am not going into the details, but except the fact that we have to use oxygen, we have to use palladium, and we have to use high pressure hydrogen. It is not only expensive, it is also dangerous and high temperatures. All right, the idea is that if you can use a photocatalyst and you can get oxygen molecules from air, Somehow, if you can put 2 protons, it becomes H2O2. It's a very simple reaction. So we have oxygen and we have 2 protons, so we need 2 electrons. Now, if you can excite 2 electrons and convert to protons, they combine and they will end up giving hydrogen peroxide. There is another way we can get hydrogen peroxide, that is from OH ions. If OH minus ions, if somebody can take 1 electron, it will become OH dot, and 2 OH dot will combine and give H2O2. So H2O2 can form 2 ways, by reduction as well as by oxidation process. All right, this is another catalyst. Again, I want to show, we have used it for hydrogen peroxide production because it has vacancies. It has negative vacancies and oxygen vacancies. That is where oxygen sits there, and it gives very good amount of hydrogen. When I say it is very good amount of hydrogen, this is a comparison table, and you see that in air, using our catalyst, the activation is very, very good compared to whatever is there in the literature. Extremely good. All right, then we started using it on a regular basis, daily basis. So as the date passes, again you can see that its activity is increasing. And by the time it reaches about 20 days, its activity is more than 2 times. And again you can see this, it's a good catalyst, already a good catalyst, but again you see this self-activation, and then it maintains there. Now we have data for about, say, 3 months, and it maintains the activity for a very, very long time. Okay, and we looked at the mechanism very briefly. What different mechanisms say that we have oxygen vacancies, and where oxygen get pinned up, and more oxygen get converted to O2 minus. You see, when a photocatalyst takes a light, it produces excited electrons. This excited electron gets converted to oxygen. It forms O2 minus, and this is a signal for O2 minus. You see, this is for a fresh catalyst, and this is for the activated catalyst. So it produces more O2 minus, O2 dot minus radicals. Okay. All right. So what we figured out is that why this happens is that, again coming back to the same thing what we discussed, we have a catalyst where we have Bismuth oxygen bonds and other metal oxygen bonds. Now if you take into account all the different bonds, it is the metal Bismuth oxygen bond which is the weakest. Now this oxygen and bismuth slowly starts coming out from the surface. Okay? At this time, we have some pits on the surface which we call vacancies. Okay. Now you look at here this XPS analysis. In XPS analysis, what you see is that the amount of bismuth is going down slowly, showing that actually bismuth is going from the surface. Similarly, you can also, 3 minutes, I'm done. So here also you can see this is an oxygen peak. Again, without going to the details, what you can see, that green peak is coming down, but the other peaks are actually coming up. The other peaks are water molecules or oxygen getting absorbed on those vacancies. So both of them shows that bismuth is gone, oxygen is gone, and other oxides, water or O2 is getting absorbed on the surface. Now it is going to the solution. Now you look at the solution, and again, solution, you actually figure out that bismuth has actually gone to the solution. It is not there as much in the catalyst, it has gone to the solution. All right. There are some more studies. I think I'll skip this one. You can look at the bismuth oxygen, the number of bismuth and oxygen bonds, okay, before and after catalysis. This is something called EFCS analysis. And you can, if you look at this data, you basically understand the number of bismuth oxygen bond has gone down after catalysis, and which is a good thing. Okay, you look at the crystal structure, and again you see the surface slowly becomes amorphous because bismuth and oxygen is coming out. All right, and then the final, what I want to emphasize is that when these metals and oxygen come out from the surface, initially we can assume that they form defects on the surface. But these defects are very complex. These defects, they have a society. They don't stay all alone. They sometimes come together and form clusters. Okay? Little bit of more details. When you remove one oxygen, it becomes positively charged. If you remove one metal, it becomes negatively charged. our surface is negatively charged. Okay, our data shows that it is negatively charged, which means that we have more amount of zinc, bismuth, which has come out from the surface. Now, this is something called positron annihilation spectroscopy, in which you use positrons, and positron goes and hits on your material, and it reacts with the negative charges, okay, on the catalyst surface. And if you look at its decay, how these positrons get decayed, because it neutralizes by the negative charge, you can figure out what kind of defects these materials have. Now, what we figured out is that as the time passes, we had individual vacancies. They come together and they form vacancy clusters. And these vacancy clusters are negatively charged. So, as a consequence, we have more and more oxygen vacancies on the surface. So, oxygen comes and sit there because oxygen vacancy was there. The metal was hungry, oxygen can sit there. And therefore, it gets converted to superoxide radical, and then it gets converted to H2O2. Okay, that is the origin that why we get more and more oxygen molecules. So, what we saw is that for 30 days of catalysis, the catalyst keeps improving, okay? And this is what we call self-activation. And we find that it's probably the only example where you see a catalyst which is already very good, but keeps improving with time. And the origin is that surface reconstruction, selective metal leaching, and oxygen leaching. And therefore, you have more oxygen absorption and more reactivity. So, we started with this question, does a good catalyst necessarily go bad with time? But here we see that actually it improves with time. Thank you.
I hope you all agree with me. Actually, it was a very wonderful talk, Professor Ujjal K. Gautam.
Thank you.
And it's actually fascinating to see that the decomposition of rhodom in process of photocatalysis, and of course, on using this catalyst, it's actually the efficiency is increased. Okay.
Thank you.
So, please join me to give him a big round of applause. Thank you.
Thank you.
Now the forum is open for discussion.
Sure.
So please actively interact with you.
Well, very nice to see this new dimension that you have introduced to catalysis. Fabulous. Very nice. Very different directions are coming, and you talked about one of them. I want to go back at the beginning where you talked about piezo catalysis. So two questions I have. These days, droplets are becoming very, very...
Which one, sir?
Droplets are becoming very interesting. Droplets.
Droplets?
Yeah.
Yes.
And when you have ultrasonic irradiation, some activation, you do get bubbles.
Yes.
I was wondering whether any of these phenomena that you talked about are influenced by bubbles,
Yes.
cavitation, and the surface or the interfaces.
Yes, exactly. It's very much the origin of pressure in ultrasonic noise is actually bubbles. So we have bubbles means we have high concentration regions and low concentration regions. That is what is a bubble. Now what happens? These bubbles collapse, and then bubbles become bigger bubbles as time passes because multiple bubbles comes together. At some point of time, the surface tension becomes so strong that it collapses. The idea is that if your catalyst is caught inside the bubble, when the bubble collapses, all the molecules will come rushing, and then they impart kinetic energy on the catalyst, and that is the origin of pressure.
So you do see that effect.
That has been the understanding, but we have not proven it, but that is the mechanism of ultrasonic pressure transfer.
So the other related question was related to the charges that you introduce on the electrode surface in this very same activity that you talked about. Charges are in. Mm-hmm. What is the origin of these charges? Because the droplets are supposed to be producing, chemical bonds are broken at the interface, which produce these ions. And therefore, my question is there any bubble-induced processes involved in the charging?
Yes, very interesting question. Again, the answer is I do not know. But the conventional wisdom is that these are piezoelectric materials because they are non-centrosymmetric. So if there is something non-centrosymmetric, if you apply pressure, it is going to develop charges. And then we have positive charges and negative charges because they are exactly single crystal. Each particle is a single crystal.
But this is happening in solution.
In?
Solution.
In solution, yes. Yes. The assumption is that if the crystal is in the solution and the molecules are exerting pressure, it has no choice but to develop those charges. And when those charges get developed, the band bends because the electrons near the positive charge, their energy will be down because of attraction. And the opposite side, they are going to go up. So it is very similar to electrochemistry. You are adjusting the potential, but by pressure, not by electricity. Now, once you twist this reduction potentials, they are capable of doing oxidation and reduction reaction within the crystal.
This happens only in water or in all solvents?
It should happen anywhere. And we have seen, but they are aqueous solvent, not necessarily water. They are polar solvents, but non-polar, it should also happen.
Thank you.
So, Ujjal, very nice talk. So, to add the Professor Pradeep questions, that I think that we have the dipoles.
Okay, yes.
Yes. So, the dipoles is that one origin, which is the surface, one side is positive, another is the negative.
Yes.
Like say that, let's say lead titanate,
Yes.
like this kind of all the ferroelectric crystals.
Yes.
They have the positive and the negative charges
Yes.
that happen.
Yes.
Then sometimes it's called the screening charge effect. The screening charge effect, you potentially don't need to the band bending.
Yes.
It can eventually have the positive and negative charge, which can help you to catalyze the reaction.
Yes,
But
yes.
some cases in the pressure which does not achieve that your valence and conduction band, that time the band bending occurs and
Yes,
eventually
yes,
it happens.
yes.
That is
Yes.
some small clarification there.
Yes.
So my question is that, as you mentioned in one cases, that when you have the photophysical systems, you eventually that you are telling the homo level is the only thing, and your the
In piezo.
valence in piezo.
In piezo.
So is it a better way to talk like this? Because you see that you have the, because of your dipoles, you have the positive and negative. When you are shining the light, you are enriching by the light to that, either means the conduction and valence pole, and that is the synergistic effect. Because you already reach the charge separated state in the piezo, where you have the positive and the negative. Then when you are shining the light, that is, you are enriching that electron carrier into that your conduction band, and also that you hole in the valence band. That way,
So I think, yeah, slightly we differ here. We say that, yeah, because of the dipoles, we have valence bands and we have positive charge and negative charges.
I'm not telling that there is they reach to the two separate states.
Yes.
Where that's why the catalysis water splitting is happening.
Yes.
Then if you have the sunlight, that is extra things you are getting from the light.
So
That way I want
what
to
my
tell.
calculation shows is that the pressure is no way can excite an electron from the valence band to the conduction band. The pressure is not sufficient. It can only bend it.
Huh.
But once it is bent, if you start shining light, the electron will actually go from the valence band to the conduction band. So let us understand it this way. If it is from the valence band to the conduction band, for example, let's take a simple example, zinc oxide. What essentially we are telling is that the electron is going from oxygen to zinc. Because your conduction band is made of zinc and valence band is made of oxygen. So when you excite, it is essentially going from oxygen to zinc. But in this case, when you have band bending, it remains in the zinc. Even if it is positive charge, it is not charge, it is just the potential.
Yeah,
it is like
the
platinum electrode can have potential, negative potential or positive potential. It is not the charge.
It is the dipole set.
Yes.
Let's discuss after the talk. Yeah.
Okay.
So if you have no more questions, this is a time to express our gratitude to Professor Ujjal K. Gautam. So on behalf of ECHS Farook College and my own personal behalf, I request Professor Ujjal K. Gautam to accept our token of love and appreciation.